So we've already chosen to use binary encoding, where we use, for example, with 4 states, 0, 0, 0, 1, 1, 0, 1, 1. And that was a unique encoding for 4 states. But it turns out that we didn't have to use that, right? We could have chosen other unique encodings. And one other common encoding is called one-hot encoding, where we have 1 bit of state for each state. So we have 1 state bit per state, and it's one-hot in that only 1 state bit is high at any given time. So for any given state, only one of those bits will be high. So for 4 states, we'd have 4 state bits, and S0 would have the 0th bit high, S1, S2, S3 would have state bit 3. So again, we'll still call this S sub 3, state bit sub 3, but it corresponds to the state named S3. And this does require more flip-flops. Now we have 4 bits of state, where for 4 states before we just had to have 2 bits of state. So that's a downside, but often the next state and output logic is simpler. And so that outweighs the need for a little bit of additional hardware. So we can look at our state transition table again, and this is also called a next state table, by the way, straight state transition table or next state table. We use those interchangeably. And we're going to look at the same table from the traffic light controller example and use a different encoding. So now we're going to use one-hot encoding. We have 4 bits of state now, S sub 3 to S sub 1, or S sub 0. So S sub 3 to S sub 0. We have 4 bits of state. And only one of them is high for any given state encoding. So S0 has state bit sub 0 high, so state S0. State S1 has state bit sub 1, S sub 1 high. State 2 has S sub 2 high. And state 3 has S sub 3 high. And so only 1 bit of the state is high for any given encoding. So now we just replace our encoding. So anytime we see S0, we put this encoding. Anytime we see S1, we put that encoding, and so forth, just like we did before. The unencoded table doesn't look any different. It doesn't depend on what encoding we use. So now we replace S1, 0010, S2, 0100, and so forth. And now we can just the same process as before when we use binary encoding, write equations for each of the next state bits. So S sub 3 prime has a single one, so sum of products. And here's the common error. And so look at this and say, okay, well, I can do that in sum of products. S sub 3 bar, and S2, and S1 bar, and S0 bar, and T sub B bar. And we're like, okay, cool, that is sum of products. But we've forgotten the whole advantage of one-hot encoding is that, well, we know because of our encoding, we know that if S2 is high, I already know that the other bits are low. By definition, I've made it so that if S2 is high, no other bits can be high. All the other bits are low. And so the correct equation, they're both functionally correct, but the minimal equation is S2 and TB bar. We don't include the state bits that are 0 because we already know because of our encoding those bits are 0 if S2 is 1. So we say S2 and TB bar. And we can do the same for the other bits, the other state bits. S2 prime is going to be, well, S1 or S2 and TB, or that's it, two ones for S2 prime. S1 prime is going to be S0 and TA bar. S1 prime is going to be S0 and TA, or S3. And so we look at this and we say, oh, there's our state transition diagram. And you'll notice that, well, there's a correlation here. So S3 prime. So the way we get to S3 as the next state is if we're in S2 and TB is low. And so it also helps us kind of debug or double check our equations. Another example, how to get to S2 as the next state, state 2. Well, we can either be in state 1, that's a way to get there, or we can be in state 2 and TB can be high. That's the other way to have S2 be the next state. And so often, again, this logic is simpler, and we can do the same thing for the